Thank you very much, Oliver. So first of all, of course, I want to thank the organizer for this amazing conference and program and to give me the opportunity to talk about this project that has been going on for a few years. So the main goal of this talk will be convince you after these two amazing talks that we have this morning that there are some physics beyond non-reciprocal systems. So it's hard, but I will try, okay? So first of all, let me thank the collaborator. There have been many people involved. First, of course, the PhD student here, and of course, our amazing chairman, Oliver Duchot, and our amazing previous speaker, Quentin Collet and Vincent Demery. So, okay. So, for me, this is a very, very illustrative system. This is a colony of cells. In this experiment, what they did, they track how these cells move around this, in this confined system. And we can observe that the paths that these cells follow are kind of liquid-like in this regime here. But now once you increase a bit the density on the system, something really amazing takes place. And we observe the appearance of this kind of sustained oscillation in this system, okay? And this, for me, is the manifestation itself of the appearance of the effect of elasticity or stresses that are propagating in the system. And this is what I will refer as an active solid, where this interaction, this elasticity or stresses are important to determine the physics of this system. This I'm showing here other two very interesting experiments. Probably Julian will talk about this later. This is another biofilm there where they observe this beautiful oscillation rotation. And this is another nice experiment. It's kind of a 1D channel where they observe something like some active waves propagating along this system. Along this, there's another kind of phenomena that also we observe, actually, Corentin showed us a bit, that is the locomotion of this active solid. But in particular, I want to talk about this very simple and beautiful animal that is this trisoplaque adherens, which lack of a central nervous system, but still is able to develop very complex behavior. So in this system, each cell tries to crawl, and when we put all of them together, they find a way to follow some particular path, some collective behavior that could be just translational. Here is stop for a minute because I think that is sitting, then move. Also, they can perform some rotation and some different kind of behavior. Here's another experiment, another group, and this is just, they measure, this is the vector field. So this case is when the system is just translating, and when this is all these colors because the system is rotating. So they observe that depending on the size, this can translate, rotate, or if the size increases a lot, then it becomes very complicated for the system to self-organize, and so the system doesn't move anymore. Okay, so these are the kind of systems that we're interested. However, all of these systems coming from biology are beautiful, but extremely complicated to understand because there's a lot of different interactions that are taking place and that you need to consider. So what I want to do is to simplify this to more physical systems. So, and actually the first to do this, I will say I need to cite this work of Silke Henke-Frey and Cristina Marchetti, where they, for the first time, I think, or one of the first work where they did this model of active particle, and they studied the dense regime, and they observed that if they increase this packing fraction, they observed that there is a jam state where the system already showed this kind of actuation or activation of the fundamental mode of this solid. Okay. After this work, many others have shown different, with slightly different equation of motion. They observed different kind of phase diagram. This one to name a few of them, and since everyone want to have a phase diagram, we also did a phase diagram. Okay, this is for a slightly different system. This is the very, very simplest model that you can imagine, where the orientation have some quench disorder, so it's essentially infinite persistent limit, and we did this to define this phase diagram. and we've observed some very interesting results for this active solid that I will try, if I have time, to come back at the very end of my talk. But for now, I want to focus on the fact that all of these different systems, they show a solid phase or a jammed phase, and this is the regime that I want to describe now. The case that we are very deep inside the solid regime where no plasticity taking place. Okay, so how we did this? Well, we introduced this very simple mechanical model. This is what we call this active solid model, where the topology is fixed, okay? And some of you probably have seen this before, but this is just a bunch of X-bag. There are these cockroach that have some motor inside and make them to walk around. We 3D print this ring. We put it inside in order to allow them to turn freely. And then we put some spring and attach all of them and create our amazing active solid. That, of course, is way simpler than the one provided by the nature in biophysics. However, they still display many of the exciting behavior that we observe in biology. So we can see from collective motion. Here is rotation, collective motion that is appear here. This is kind of an active mechanism that the system is contracting and expanding, and also this active actuation or self-sustained oscillation that I want to describe. So these are the kind of phenomena that I want to describe in my talk and try to have a better understanding of these phenomena. Okay? So I want to start with the simple case. This is the very simple case when we have floppy mode. What means floppy mode? That the system can evolve without changing the length of the spring. Okay, so essentially have zero energy mode, our solid. So here, this system, I have 3 floppy modes, 2 translational and 1 rotational one. And when we can see from here that depending on how we start, the system can pick translational or rotational. And even more interesting, I think, that you can see that when this hit the wall, it's amazing that the system immediately reorganized, point to the other direction, and start to move. So it's always looking for the floppy mode of this system. So what I want to understand is we can understand what controls this activation, or we can design some new system where we know or control which mode will be activated. Okay? Perfect. So let's go to the equation now. The equations are very simple, and we can compare directly from the experiment. This is the standard overdamp active dynamics, drag force, self-propulsion force, external force that will be, in general, this spring, no? And then the question, this is the very standard, but then the question is what will be the dynamic for the polar vector in terms of this angle theta I? Theta I just said the polarity angle. So we use something that has been used for a while, that is this self-alignment torque, or just self-alignment, that says that the polar vector, this vector n, will tend to align with the velocity of our system. Okay? This is what is written here. And the distance that required for this alignment is this LA. So, and we can measure this from the experiment. We just take our ring with the X-back and we push it in this direction, so the system will align, and that distance is LA. Very simple, okay? Now, it's interesting to know that even though this equation has been used already for a long time, 1986, we couldn't find any microscopic derivation of this alignment equation. And so we did that. It's very simple, actually. We did that, and this review paper is just in the appendix of the review because it's not the main subject, but we can do that from just a mechanical point of view. And what you find out is that this self-alignment is something that shows up naturally once the center of mass of your X-back is slightly different from your center of friction. Okay? And the alignment length is just proportional to essentially the area of your system divided by this distance d. So this is very simple, and we understand pretty much everything. And so now we just add some, to be more realistic, some external noise, delta correlated noise, and these forces are just given by the spring of stiffness K. Okay, so of course we were not the first one. There's already a few others group that have done work with similar set of equation, and in all of them they observe that there is some emergence of this collective behavior of translational rotation. But what we want to do is to try to understand a bit more what are the mechanisms that control this, and if we can control or design a particular active solid that perform particular task. Okay, so the first thing that we realize, to have a better insight, is the following. Here we have a single system that is spinning at the center, so here we have a single floppy mode. Okay, and so this is rotating, and we measure how activated are the different, how excited are each mode in this system. So this one here are just the overlap between the different mode of our elastic material with the polarity vector, that is a signature of how much are excited each mode. And this one represents the first mode, that actually is a zero mode, that is just the rotational mode. Okay, so I have zero energy, and all of the other represent the other mode. And we can see that actually only the rotational mode is strongly excited, and all the other are order of magnitude less excited. So what we realize is that we can neglect, for this kind of behavior, the elastic excitation. And that allows us to simplify enormously our problem, because then we can consider actually that there is no elasticity and the system is not deforming, but it's just rigid interaction. So still we have stress that propagate along the system, but without elasticity. Here we perform some numerics using just exactly rigid system, and you can see the bond, the color bar represents the stresses, and you can see that this is enough to organize this system. And now the equation becomes way more simple. I don't want to go into detail, but essentially depend on the number of floppy mode. This is the stresses or the forces depend on this sum is over the different floppy mode. And when we have done this, now we can try different system with different number of floppy mode. This one here this is a honeycomb lattice. We have plenty of different floppy mode. The dynamic is rather complicated. This one here is also very interesting one, and I will come back to this one. This is a system that have two floppy mode. One that is a rotational one, another that is auxetic one. That means that the system can contract or expand without changing this length of the bond. Okay, so can we control and sign this collective behavior? That is what I wanted to know. Okay, so the starting point is this is the stochastic evolution. I don't want to go into the detail. This is just the Fokker-Planck equation. It's not really relevant for what I want to discuss. There's only one important point, that this equation or this system have two-dimensional parameters that are controlling the dynamic. The first one here, this is just the ratio between the noise, okay, and the active actuation, or the active force, sorry, not active actuation, the active force, the noise and the active force. And the other one, and that I'm more interested on, is this PR, that is the ratio between the alignment length and the distance between bones. And this dimensional parameter tell us, if we think in time scale, is the separation of time scale between the system aligned on each of these polar active polarity or the polar angle aligned with the velocity, compared to the time that these floppy mode are being deformed or the system is evolving. So in many cases, when we have that this parameter is much smaller than 1, something very nice happen, and actually is that this Fokker-Planck equation now can be written in such a way that, depending on potential energy, without going into detail, that can be exactly solved for a given configurations, and the solution is given by a quasi-equilibrium state. So we can map in this limit when we have this separation of time scale between the time that the system relaxed to align compared with the evolution of the system to a equilibrium state, okay? And given this, we can now go to what we know from equilibrium physics, and we can calculate the free energy, the Landau free energy, and we know that the dynamic now will be given by the minima of this free energy. So We calculate this free energy in this system. These mu are represent the order parameter. In particular, just go to a simple example. If we have this system here where we only have rotation, this is phi. This order parameter is just the velocity of rotation, phi dot, okay? And so we have our Landau free energy for this case. We found the minima on this system. That will set which will be the angular velocity of our network. And since we know what is the angular velocity of our network, we can then evolve our system under that constraint. And so we find some adiabatic approximation that allow us to establish this dynamic. Now let me show you 3 examples. The first one is extremely simple. Is when we have the one that I showed you at the beginning, where we have pure translation. So here you can consider a system like having a periodic boundary condition if you want. So in this case, you have pure translation. The solution of this equation are exact, and what you find is that have an exact mapping to a mean field XY model. And why is an exact mean field model? Is because since we remove elasticity and we have a rigid system, what happens is that the information can propagate infinitely in all directions. So it's like a fully connected model. So this is a very nice realization of a mean field system when we are in the rigid system. Now, the question, what is the effect of elasticity? It's an interesting question. We are working on that, but I don't have so far a result. Okay. So now, a bit more interesting case, when we have translation and rotation, this is now the free energy. And you can see that we have different minima. This one corresponds to translation, this one to rotation, and we can see how our system is moving from, now is rotating, and then we'll jump to a translation minima, and this is how we can understand, and if we define or we design this with different system size or control the noise, we will know which will be the barrier that we need to jump, and we can design as solid as we want. Okay. The final example, and I want to just give you an idea. This is a bit more complicated case when you have auxetic and rotational mode. Then the Landau free energy now depend on the parameter of this auxetic angle that we call gamma. Here is the Landau free energy. This is a control plot. This point here represents the minima of this free energy. And I'm showing this figure is changing depending if I change this gamma from 0 to 2 pi because it's an angle. And so I can find all of these different minima. So what we do now is that for each given gamma, we find the minima, and then we can define the rotational of this auxetic mode, and then that allows us to evolve our system to determine the statistical dynamic of this more complicated case. And this is what we obtain. This is just to show you, I mean, it's worked pretty well. The black is pretty well. The black is just the theoretical result. The other one are the experiment, the numerics, sorry. And we can see something very interesting here. We have that the activation of the auxetic and rotation mode take place at different times. So if we start to decrease, this is like temperature, we start to decrease temperature. First, we start to activate the auxetic mode, or this compression or expansion mode, and only at much smaller temperature, this 0.02, we start to activate in the rotational mode. Okay, so this is a more complicated example. Of course, the idea is this generic theory we can apply for a mode that, any kind of floppy mode that we have. Okay, so now let's move to the case where we don't have any floppy mode. Okay. If we don't have any floppy mode, we have an active solid under some confinement. As we can see here, we observe this sustained oscillation. Now, in our system, what we observe is a very nice transition between a frozen state, that is this one here, to an actuation, to an active actuation state, where the system is performed this sustained oscillation or active actuation, as you prefer. So the question is, what control this transition? Now we don't have any floppy mode, so the elasticity, of course, become important in this system. And so the set of equations now are slightly changed. I will forget about noise. It's not really relevant. And now the forces, now I need to introduce elasticity, so that introduce a new dimensionless parameter, that is the one that controls the physics here, that is given by the ratio between the alignment length and the lasting length. The lasting length is just the distance that one of these X-back move once we turn on the motor here. Here is the spring, so when this is turned off, this is at this distance, then we turn on, this displaced, and this distance is just this elastic length. So this quantity here is now what will control this transition between frozen and active actuation. And this is what we get. This is a very interesting result. We can see, this is here, the data with the error bar are the one from experiment, the other one are from full numerical simulation. And what we'll see is that this transition, well, we have a frozen disorder for a small value of P, a collective actuation of self-sustaining oscillation for a large value of P, and there is some region in between, there is some heterogeneous region that some kind of chaotic or disorder dynamics taking place. But what is really interesting is that this transition actually, it changed a lot depending on the geometry of the system. This is for a triangular lattice, this is for a Kagome system. So if we try to understand a bit more, this kind of behavior, what we do is we take the harmonic approximation. Okay, so we take the equilibrium position without activity, and we assume that displacement are small around this position. Okay, that allows us to write the force in terms of the linear elasticity, where this is just the dynamical matrix that contains the information of the soft mode, sorry, not the soft mode, of the elastic mode of our system. These are just to name a few of the elastic mode of this network. Okay, and from this, again, we measure the overlap of this different mode of this system with the polarity vector to track which mode are being excited. And something very interesting happened. In the triangular lattice, actually, in both cases, what you observe, there are two main modes that are excited. Now it's not one, but it's two modes that you need to excite. In this case, it's the number 1 and number 2. In this case, number 4 and number 5. And the other very interesting thing is that not always the low energy modes are the ones that are being excited. That is something very common now in physics. If you have some coherent strategy, what you do, you excite the lowest energy mode. Here, actually, you don't excite the very lowest energy mode, but you excite the 4 and 5. So the question is, why this is happening, and can we say something about this? Well, this is not fully solved problem for us, but we can give some idea about this mode selection. So to do this, now we write the equation using linear elasticity in terms of this dynamical matrix. And so there are two different regimes that we want to discuss. Discuss first the frozen state. There is the regime where the hexback seems to be frozen. Well, there is some small noise, but it's frozen. And in this regime, what you can show is that actually for any given polarity distribution that you give initially, you will find that an equilibrium solution exists. So it's from the dynamical point of view, it's an interesting system because you have an infinite number of fixed points in your problem. So the question is then about the stability of this fixed point. From the other side, when you have this active actuation, you are in what we call the chiral phase, and there are questions regarding the nature of this transition, why you pick those two particular modes, and if we can understand a bit about this spatial heterogeneity. So, just to give you some general idea, we first did some coarse grain or mean field model that for this is for the local average of the polarity vector is this M, and if we assume that we make some assumption, among them is the force, we assume that we excite two homogeneous modes, then we can end up with some kind of simple, or rather simple phase diagram showing that there is here the frequency of oscillation go from 0 to a non-zero value, and there is a region of coexistence between m equals 0 that will correspond to frozen state with the active actuation state, and the amplitude of oscillation actually is interesting. It's jump from 0 to a non-zero value, so it's have this continuous jump, the amplitude of this equation. Okay, so that it's a mean field version, so give us a general idea, but of course the story is far from over. We have this heterogeneous regime that the mean field version doesn't capture, and we understand now that this comes from the fact that there is a very strong constraint in our system, that is this radius of rotation of each of these hexbag need to be larger than 1. Okay, and then that constraint have some problem when you approach to the boundaries if this amplitude of the self-propelled force is not strong enough, because it makes that here in the middle they can move in some radius that is larger than 1. When you go to the boundary, you cannot reach that value because it costs too much energy, and so the particles in the boundary start to have some more random or chaotic behavior. Okay, and finally, perfect. Finally, just a brief comment about the selection of these two particular modes. It's something that we still don't fully understand. The best that we were able to do is to find a bound that give us that all the fixed point, since I told you that we have infinite fixed point, and what we found is that there exists a bound above which we can prove that all of these fixed points become unstable. So if they all become unstable, you expect that something needs to happen. That could be whatever, I mean, active wave, active oscillation, whatever, but something needs to happen. And what is interesting is that this bound, or to construct this bound, you require two modes, any mode that you want, and that gives you a bound. Okay, so this, we can do it for every bound, for every mode. But what is interesting is that the best value of this bound, the one that gives you the minimal value if you want, is precisely that one that is precisely using the mode that are selected by the dynamic to be excited. Okay, so the best bound it's equal to this mode selection. And from studying a bit more this, the shape of this expression, it seems to be that the modes that are selected are precisely those ones that are more locally orthogonal. That's what we observe. Okay, so I have 3 more minutes. Perfect. So now let me jump to what I told you at the very beginning. If we start to increase the activity of the active forces, at some point plasticity will take place, no? And once the activity take place, the plasticity take place, we want to study precisely this transition between the solid state to a liquid phase. Okay, and we did this, and we encountered a lot of problems. We were doing this, we're just increasing this. Now we are taking we are considering now a system of particles, not spring anymore, just particle with some repulsion, and each particle have some polarity vector that is quenched. It's a quench disorder with some self-propulsion force. And now, if the force is very low, we are in a jam regime, but then we increase the F, and the system start to flow. We want to measure the critical behavior or whatever, how is the transition, and the data was pretty bad, and so we produced some movies, and something showed up that actually we should have expected. But since I'm coming from the rheology world, I was not the one expecting that. Took some time, actually. This is not from the very beginning, but from anyone in the active world, it's something that I will expect. It's taking some time, sorry. But you start to see that you start to create some void that is essentially just MIMS, no? But in the other way around, usually what you have is a dilute system, and you create some cluster. Here you have a very dense system, you start to create some void. And this was destroying all of our data, so for that reason we were not able to understand this transition. So then we had to work harder, but after some time we found that actually exists some regime where we have a real liquid without phase separation, but this is a small regime. So now trying to measure here a critical exponent was not easy, but we did some work here. And we merely have this liquid plus gas is just MIMS, okay, phase separation. But what is interesting is that, okay, so this is something different from yielding transition for a shear system. And if I take a system and I just shear, I will never end up with these MIMS, okay? So it's much simpler. We have here a huge range to study the transition between solid and liquid. So, okay, but now we find a region with liquid, and now we try to study this transition, and as in the case of yielding, of shear system, it's very nice that we observe that actually this transition is controlled also by avalanches. This is just the velocity field, and we can see each of these of dark is because there is some buckling instability, and you see these avalanches, which growth is increasing when you approach to this transition, okay? So still controlled by avalanche. However, when we measure not all of them, but many of the critical behavior of this system, I don't want to go into detail, we observe that the exponent actually differ from that one under shear or passive system. So this is another example just to show that there is something deep inside in the way of active solid evolve that are different from passive system, okay? So, and with this, I finished perfect in time. I hope that I convinced you that there is interesting physics in this active solid. Thank you very much.
Okay, so if we enter the question session, we start with David.
So your active solids are all amorphous. You have a binary mixture of two different radii, so you make it amorphous.
Yeah, in that case we did amorphous. Okay, let me tell you very briefly the story of this. Actually, I'm coming a bit from the rheology. I work a lot in jamming, and we want to study yielding, and they say, okay, let's think a way to do yielding in such a way that it's isotropic. Okay, let's do this, and then we realized that we are working in active systems. So why is this bi-dispersed? Because usually you want to avoid crystallization. So for that reason you do that. Yeah.
Another question? Yes, please. If you can move to the microphone.
Can you speak a bit more to the mode selection when you have confinement and you're selecting these pair of modes? You said they're locally orthogonal.
Sure. Okay, so let's say the following. We don't have this is not a proof, okay? And this is not a proof that the system will select the most orthogonally, local orthogonally mode, okay? But this is what we observe in the numerics, we observe in the experiment, and what we can set from this bound is that the best bound, this means the value here, if I pick I need to pick two modes. If I pick any couple of modes, this value here will be larger than the one if I pick the two locally orthogonal, okay? And that is, those one are precisely the one that selects. So that's what I can say. I can't say anymore. I mean,
it's observational.
It's an observation. I cannot prove the formula.
So is this like right above the transition in your control parameter? Like further up, is this still like
this is the value of the bound, and this is 1.49, 10883. Let me go back. So it's not perfect, but if you see, this is 1.4. Where is the other one? Jesus. 1.49 is
further up, you're still picking up only these modes?
That's a good question. That's a good question. Huh? Yeah, you mean, this is where I'm going the other way. So if you want to continue increasing this way here. Well, that's a good question. I don't know. What we believe, okay, if you have a system, at least for instance, if you have a system that is large, okay, that is not square in the case of square, no? At some point, and if first you have this active actuation, then the entire system is oscillating. But at some point, something happened, and you have that some breakup of your phase. So it's not no longer a constant phase, and you start having waves. Okay, and then it's a bit more complicated. Actually, so the answer actually in general, no. But so here is we are working on this right now. This is what happened if you have, this is a one-dimensional case, a very simple case. So here, your parameter, you are in the region, you have this actuation that is everything oscillating in a synchronous way. If you continue increasing, that phase is broken, and you have start having some active wave. There are probably some nonlinear waves. Yeah.
In this place where you get void condensation, MIPS,
Yeah.
The dense regions are always liquid. They themselves are never solid, even though their density must be much higher than the phase out of which they condense.
Sorry, I'm not sure.
Go back to your MIPS.
Here? Here.
Yeah, so you start out with some density, and now you start undergoing void condensation. So the non-void part is now much denser.
It's a bit higher.
It's never solid. I mean, you would think that maybe...
I don't, well, it's a bit more complicated to measure, because around the void that you will have particles that will be going on and off, so yeah, you need to, yeah, it's a good question. I haven't, yeah, that's a good question. We haven't checked, that's yeah.
Thanks for a nice talk. So I have a question on the translation and rotation part.
Yeah.
Where the system was translating and then spontaneously rotating. So have you characterized the time scales involved? Like how, I mean, one question is what leads to the transition between those minima and minima?
Sure, I mean.
So that is one, and have you characterized, or can it be analytically or numerically solved? Like how long it runs, how long it translates, and what leads to rotation?
Well, we haven't, but we know that this is just given by the Kramer escape time. So once we have, so we have some noise, we have some, what we can do, because we have the perfect free energy, so we can measure numerically, or in some cases actually analytically, the high of this barrier. And so using the standard Kramer escape time, I mean, you should be able to do that. We haven't checked it, okay, but we should be able. Huh?
That would be Gaussian excitations, and you don't have the Gaussian excitations. So I think that the Arrhenius barrier would give you that time.
I think so, yeah. That is a bit different. It's a bit different because here the noise is true that it's in the angle. That I mean, but we can. But I'm pretty sure. I mean, at some point we did something. We didn't continue, but it's something that we should find. But I think that is just that. I mean, this is just free energy, and then the time to escape from one point. Maybe it's not exactly the range, but it's something that you can compute in a similar way. You have all the elements there. Yeah.
Also, perhaps I missed this point. How important is the geometry here? Like, what if I remove one of the ball? Like, what will happen in this case?
That's a good question. That's a good question. Well, in general, I mean, here these are very symmetric. If you remove some of them, then the rotation, it will be a bit different. But you can always find a center of rotation, and well, the translation won't change. So you will usually have the same kind of behavior, usually, okay, but not always. Let me show you an example. Actually, if I didn't, maybe you notice here, but here there is a small difference between this one and this one. I don't know if you realize there is one missing X bag in the middle, because if we add this X bag here, this configuration, the rotation will become unstable at long time scale. So start to rotate and at some point become unstable and move. So usually it doesn't change much in terms of the floppy mode, but in some cases can give you that one of these modes are unstable, and so you can.
Complete follow-up. What if we just join two balls together? What happens?
Good. We know. Actually. Okay, so there's a very interesting question, and now we are working actually on that direction, because here, this free energy, actually we calculate once we consider the large n limit. And here we don't have n large limit. Okay, so now the question is what happens when you have finite size effect. But what is interesting is that if you have extended floppy mode, actually you can, it is like a fully connected system, and so you can, you won't have the free energy, but you still have kind of the full integral that you can solve. So we can actually say something about that system in the same limit that PR is small. Let me show you something here. So what happened, I think that I don't have it here, but here, for instance, this is a nice example. Here's the importance of finite size effect. We know now that finite size effect can lead you to some particular orientation of your solid. Okay, so from the energy, from the Landau free energy, actually all of the orientation were the same. You have the standard Mexican hat, but when you consider the finite size, actually you could select the particular mode that the system is evolving. You're welcome.
Silke?
Yes, let me ask you normally the floppy mode condenser. So your mapping here, how robust is it? So I saw in your simulations you have extreme deformations, I think so they handle with each other. So what happens if the deformations can only be finite with a real system, and maybe if the other maybe it's not 100% floppy, or maybe something else is not as rigid. So does it survive, or is it have the effects into mix, or do you think it can carry through?
Okay, very good question. There are two different things, no? I mean, one is the effect of elasticity. I don't know if you refer to that one. We know we have run some numeric. I have it around here. I'm prepared. Huh? So this is for at least for the periodic boundary condition, at least the transition. When you this is the black curve is the read limit. The other one is when you introduce elasticity in your system, and effectively you see that there is a shift in the transition point, but you still expect to observe the same kind of second order transition. Okay, that's one thing. Another one that is more interesting is that, and that referred to some work of Olivier, is that what happens when you have, for instance, a single mode that is not floppy but have very low energy, and not two, one. Okay, in that case, I think that you can consider that one as a floppy mode along. I mean, I can show you the in the video is what at the beginning what it is. Sorry, I hear too much. Here, no, this one. This one is a nice example that you have, it's not a floppy mode, but the rotational one is the one that is the lowest mode. Okay, so it's true that then where you can consider that this is like a floppy mode up to the point that the springs are so stretched that you cannot consider it a floppy mode anymore. But we try to do this with our system, but our time scale separation that we use in our model, what tells us is that the system is not like oscillating, but it's just jumping from one state to another. So we need to consider the limit where this dimensionless parameter, this PR, is not extremely small in order to capture that phenomenon. But yeah, it's a good question. We haven't done that, but we know that it's there, but we don't know exactly how to solve it. Thank you.
I had a question on your last part on the different criticality with the quenched active forces and the shear. Do you think there's a way of interpolating between these two types of criticality by adding a finite correlation length on the active forces in the style of Peter Morton, and colleagues?
That's a very good question. We have been working on this for a while. What we measure in this case also was the correlation length precisely of both systems, and in terms of the active forces or the strain rate, and they also differ, the correlation length. I mean, the way they both diverge. The divergence in the case of shear is much faster than the one in the case of active system. But so that's what we did. Then we tried to measure what happened in the quasi-static, a bit of the, okay, so people usually think about quasi-static limit to study the avalanche statistic, and then surprisingly everything was exactly the same. So there's something in the dynamic that lead to this difference. So the statistic of the quasi-static avalanche are exactly the same. So it's something, when you go to the dynamic, there is change, yeah. So we have spent a few years trying to measure something that is called the exponent zeta that relate. We can discuss about that. We have a lot of different things there. You're welcome.
Interesting, thank you. Ying?
Can you comment on what captures the frequency of the static modes?
What, sorry?
So what controls the frequency of the synthetic modes?
You mean in the case of active actuation?
So you, in one of some of the slides you showed rotational oscillation and translational oscillation, and so for instance, in these modes, what's their frequency or the relation between their frequencies?
I'm not sure if I understand your question. From what I explained before, we don't know exactly which mode will be selected. We just can...
So sorry, here the frequency, I mean the oscillation frequency of the macroscopic one, not the probability of selecting those.
This one is, this is the very simple, what control this frequency is pi, essentially, okay? This is the mean field version, that is the simple one, okay? But give you some rough idea of how.
I tried to connect this with some of our experiments on material solid, where we found transition between translational and rotational modes, and there's always a twofold frequency jump, which I'm really talking about.
Okay.
So we try to understand this.
Okay. That's interesting.
It will be interesting to discuss that,
that's
yes.
an interesting conversation.
Okay, I think we are perfectly on time. I think as a chair I should... no, there is David who has a final question.
Sure. So you have like these Landau potentials, and you can understand a lot from that, but if you made it non-reciprocal enough, you could get chaotic transformations between rotations and translations, and could you predict such a thing? What would you need to do to get chaos?
I don't know, but yeah, it's interesting. But I don't really know. Sorry.
Okay, so let's thank Gustavo again, and let's move to our next speaker.